Okay, this is a review of the 2056 technical binder and some things that we can learn from what they published in their technical binder. Uh, I'm going to go to Chief Delphi here. If you want to look at their binder, it is published under a link here. They do this every year. There's several teams that do this. Theirs is one of the best ones here. You can look at all their CAD. You can also look at their technical binder. So this is kind of like a high level overview of everything they did with their robot. So if you want to look at all their systems and how they work, explaining their drivetrain, what their intake does, what it's made of, their straightener, coral cradle, their arm, elevator, and then they get into their climber and how they reduced weight, their electrical systems, and what I'm really interested in, their control setup on their game controller and how they did their software. This is really the interesting part for me. So how they did some of the things here and how we can learn from this. And then some of their fabricating processes and their sponsors. So that's basically what's in here. Theirs is really good. There's teams like Jack in the Bot 2910 publishes the same type of thing, but there's a lot of really interesting things in here. One of the big takeaways from 2056 is that they are a super simple team when you really look at it. There's almost nothing that they do that is complicated and that is really beyond what we do as a team or that most teams do. So things that they do, they drive their robot based on a set of coordinates. So they give it some coordinates, they automatically drive to that location. That is something we were doing this year as well. So that is something that we are capable of doing right now. They do simple 2D vision. So they can get not three-dimensional, but two-dimensional data from the camera. We are capable of doing that. They do object detection. That is something we have not done yet, but something we could learn by next year. They were using object detection to find the coral on the field. They have very smooth motion of all their mechanisms. We also do that. They probably do it better than we do, but we are pretty good at smoothly controlling our mechanisms. They do have part detection and tracking of the parts everywhere inside their robot. We didn't do that this year, but we could easily implement that using some beam brake sensors. We actually bought those this year, but we just never installed them on the robot. They use built-in encoders on their motors, the same as we did for all of their motor feedback. So they didn't use external encoders. They just used the ones that are directly embedded inside the motors, just like we did with our encoders inside the Neos. They use Kraken motors, but it's basically the exact same thing. And they use a state machine and timed robot structure. We use a command-based structure, but we could easily implement a state machine programming structure like they do, and we'll go through a little bit of that here. State machine is a method that I've seen many of the high-level teams, such as Jack in the Bot and OP, both use that method for programming. So what is a finite state machine? Let's go through this first. A finite state machine. This is a method of machine control, very popular in industry and also with many high-level FRC teams. These offer several advantages as opposed to command-based programming. It's very easy to read, troubleshoot, and understand. It is very good for implementing sequences as well. It can be implemented effectively In order to do this, your robots have to have enough sensors to be able to detect changes in the gameplay conditions, such as arm angles through encoders like we do right now. You need to be able to detect if you have parts loaded or not loaded. So you'll need beam break sensors wherever you want to detect parts in your machine to determine what should be able to happen next. So my understanding of these finite state machines, or SM as they are called, each subsystem can only be in one state at a time. There are a set of inputs, such as your controller buttons, or these sticks, or robot sensors, or vision cameras that you sense the outside environment, and that defines how you transition from one state to another. And then each of these states has a matching set of output conditions that should be happening in that state. So if you are in a certain state, all of your motors should be doing a certain set of things. So for example, this is 2056's drive system. It has 4 different states. You are either in field drive or robot drive, the way that you switch between field and robot. Is you go, if you press the R3 button, you switch from field drive to robot drive. If you press the L3 button, you switch from robot drive back to field drive. So that's just a way to toggle between these two states. If you want to go into assisted drive, that is used to pick up Coral using the camera. If you push the driver Coral pickup button, that takes you from field drive to assisted drive. If you release that button, you go back to field drive. So that's basically just a toggle back and forth, whether this button is pressed or not. And the same with the auto align function. If you press L1, 2, 3, or 4 button, you go into auto align. If you release those buttons, you go back into field drive. So that is basically just how we read a diagram like this. These are our states, and this is how we transition from one state to another. And basically, if this button is on, we switch over here. If this button is off, we switch over to here. So that's how their drive system gets defined. And then this is the operation of all of the rest of their robot. So we have the different states, and we have the different buttons and conditions that transition from one to another. If we look at this more closely, if you wanted to score L3, basically all of your robot mechanisms are in the home position. If you press the L3 button and you have a Coral present in your gripper, so you have a Coral in your gripper and the driver presses a single button, that puts you into the Coral score L3 state. And what will happen then is your robot is going to auto align to a post. The elevator and arm are going to move to the L3 position. So all those things are going to happen all at once just because you are in this state. And then it's just sitting there waiting for you to push this score button. As soon as you push the score button, it dunks the Coral onto the post. And then as soon as you push the home button, it is going to back away from the reef, lower the arm, lower the elevator, and go back to that home state. So basically their entire scoring sequence is I have a Coral in my gripper, I push a single button and it goes to the scoring position, it finds the post and moves to the right position. I push one more button to score, and I push one more button to go back home, and I've scored an L3 Coral. So that is all one person doing that with 1, 2, 3 button pushes. Okay, if you want to score on L2, it is the same sequence except they're pushing the L2 button, score, and then home. So score and home is common for all these, and you're just pushing a button to determine which level you're going to. But that takes care of all your auto align, all your elevator and arm positions, and your scoring motions, and then going back to home again. So that is the way that these state machines run. So if we wanted to translate that as to what we did this year, so let's look at an example of, let's load Coral in our robot. So we can go from home to loading Coral. We can do that just by a single button push, let's say. So let's say we just want to have one single button that does that, the load Coral button. So we're just driving around the field and we want to load Coral. So we push a button that says load Coral. So what's going to happen there? Let's say we have 4 different states. So we could have home, moving to load, loading, and loaded. We have 3 sets of motors that are involved here. We've got all of our drive motors. We have the elevator and we have the wave motor. So that controls the angle of the wave. So when we're in our home state, none of these are pressed. We don't have a target position or anything. We are holding the elevator at home. Driver control is moving the drive motors. The wave is at home as well. Once you push that load Coral button, so that's basically the transition that's happening here, that load Coral button is being pressed. Once that happens, that is going to give us a destination for our drive, and we are going to PID control move to the load position. So that's going to drive over to the load station with the correct rotation angle and XY position for the robot to head to, and it's going to end up over there. It's also going to move the elevator to the correct loading position and move the wave to the correct loading position for load as well. We are in our loading state. Once we see that we are at the load position by our field odometry, so we can put our motors for the drive into idle state at that point and not control them. And we will hold these positions with our elevator and wave. And then we are waiting to say that we are loaded. We are waiting to actually detect that a Coral has arrived in the wave. So we have a beam brake sensor here that once we see it go from off to on, we know that we have loaded. And once that happens, we basically tell the elevator to go home. We tell the wave to go home as well. And then we have transitioned into the loaded state. So that is basically how we go from home to loading the Coral, and then we are loaded and we basically are back into our home state from there. And once we are loaded, we basically jump back to our home state, and that is our complete cycle through this loading operation. So that is basically how a state machine would work. We have some inputs that we're monitoring. We have some outputs that we are controlling, and we just know if we are in this state, this is what our output should be doing. And that is what we are looking for. So inputs control the transition of the states. Motors follow whatever state we are in. That is the whole idea of the state machine. We can expand that out. We could do a more elaborate Coral scoring cycle if we wanted to as well. I won't get into that one. So some of the benefits of this, we can plan out all these states and transitions, draw them out on paper, figure all this out. We can test it. We can actually simulate this without having the physical hardware. So if we've got a RoboRio and a controller connected to it, we can program all of these states and the transitions. The only thing we can't really do is control the motors. But if we can make all the transitions happen correctly, then we should be able to fake out the sensors and the encoder positions, even just by giving them keyboard inputs for testing. And we should be able to test all this stuff or simulate it without actually having the motors connected. So we can do most of this essentially offline before the robot is built and test out a lot of our code before the robot is built, which makes it really good. The other thing we can do is we can break this up into individual tasks. So we can have 2 people working on the elevator or one mechanism and the states for that. We can have 2 other people working on the states for another mechanism and basically break it up into smaller chunks and have several different teams of programmers working on different things and programming, and then just bringing it all together because it's all kind of independent pieces that work together in the end. And you can use very similar strategies for both auto and teleop functionality as well. Let's look at vision and what 2056 does for vision. Uh, so vision, for the most part, they use a very simple form, and it has not changed very much since 2023 when April tags first came along, despite many teams using a lot of the newer features and newer capabilities of vision and April tags that have evolved since then. So they are very slow to adapt technology, and they really have a philosophy of sticking with what they know and what they know works and has been proven in competition and what they can understand. They do not use technology just because it's new, unless it has proven to be better than what they already do. So a big example of that is that they have two different cameras on their robot this year. They have a Limelight 3 Plus. So that is an older camera. That is what they're using for their auto alignment. And they have a Limelight 4, which is the new one that came out last year. They're using that for their object detection. Now that is superior for object detection, and that's why they're using it there. They're using that to detect the coral and drive over the coral to pick it up. But they are using a very simple 2D method to do their auto align. So their auto align they used for scoring on the reef, very simple method. So where we were using a 3D method where we would actually get the XY position and rotation of our robot in real time based on camera feedback, they were completely using wheel odometry to monitor where they were in the field. They were only using the camera to align and try to line up to the tag when they were scoring. So the way they were doing that, they were only getting the Y position from the camera to align. So basically, when you looked at the tag, if it was too far to the right in your field of view of the camera, you would move your robot to the right and try to put that tag in the center of your camera image. So that is a very simple way to use that. They could judge a distance from the tag based on the area of the tag. So you get a number that represented the area of the tag, and they could tell how close they were to the tag based on its size. So that is not very complex. That is technology that was available a couple of years ago, but that has been proven to work for them, and that is what they used this year. And then for rotation, they relied on the gyro for rotation. They did not rely on the tag for rotation information. And then they would only update their odometry because the wheel odometry does lose accuracy over time, but they would update that only when they were scoring. So whenever they were close to the tag and they were stationary and scoring is when they would do their update. So they were able to keep very accurate odometry updating because of that. Now, coral detection was a different thing. They used the latest technology for that. So they would drive to the rough location of the coral, and then the camera would adjust side to side to try to center the robot over top of the coral as they were driving. So they would drive directly over top of it, and that was the very same strategy they used in 2024 with the Crescendo game as well, just with a newer camera. And the final thing we're going to talk about here is their auto pathing. They had the best auto in the world last year. They were doing 5 pieces pretty consistently by the end of the year, which is pretty crazy. They did not use Path Planner to do this. They used their own code, and they did not use any type of path planning like Path Planner. This is one of the places where we kind of went wrong last year. We relied on Path Planner to do our pathing, and the results that we found was that we ended up only trying to drive forward about 2 feet, and we could not get that to work. So we would try to tell it to go forward 2 feet at a slow speed, and it would go forward at 1,000,000 miles an hour, or it would go off to the side, or stuff like that. It was uncontrollable for us for some reason, and we couldn't explain why that was happening. Now, the problem there is that we have a third piece of software that is controlling how our robot moves, and we did not understand how that worked. So when something goes wrong, we don't know how to fix it. No, they are very big on not using things that they don't understand. So all they would do is they would just basically drive to points. They would give it X, Y, and rotation points and say drive here. And then when you get there, we'll drive to our next point. And they would string together a bunch of points like that to create an auto path. So they were doing all that themselves and had great results with it. And that is the way they did their autos in 2024. That's the way they've been doing their autos forever. And it works. And that was all based off of wheel odometry as well. So for example, you would always see them set up on the field. And they would actually be out there with a little piece of like a plywood triangle that they would lay on the field here to make sure they set up in the correct angle, because that was one of the things with this is you have to set up correctly every time. So they would start at a known position every time, and then they would drive to their first waypoint, which is just a set of numbers. And they would get close to that and then say drive to my next point. And then when they would get to that destination, they would auto align, score their piece, and move on from there. So if you want to do that in a sequence of events, auto starts, update your odometry with your start position odometry so you know where you're starting from. Set your target with an in position tolerance. That means basically how close do I need to be to that point before I say I'm there and I direct myself to my next point. So these little waypoints, you don't have to be exactly on that point. You can be just close to it, and that allows them to get close and then move to the next point without ever actually slowing down or coming to a stop at that point. So you get a very smooth transition through that general area, and you can do it at speed. And then once you get to your final point here, switch over to auto align, line up with the camera, and score. They would do a very similar thing, moving to their second piece. So they would go to a waypoint, and then it would switch over to the object detection. Object detection would locate a piece of coral over here, and that would control what was steering their robot at that point. And you would use object detection to steer over top of the coral. Once you detected you had the coral, you'd break off from that and go back to your next destination point over here. Once you got close to that, you would switch to auto align and then score over here and repeat that process. And that is basically how they would string together their autos. So no path planner, no software where you just get to draw on the screen. It would just be a bunch of coordinates and actions all put together in code that they would do. And they were extremely successful with it. So what can we adopt and learn from this, and what can we apply to our own robot for next year? Number one, I think state machines are a really good way to program for a lot of different reasons that we talked about here. Second one, we need to look at vision as what do we need to do to accomplish the task that is required, and not to try to overcomplicate it. So for this year or this past year, really vision, what did it need to do? It needed to help you line up side to side at the reef. And that could be as done as simply as just putting that April tag in the center of your screen and saying we're too far left or too far right, or we're not close enough. And I will take some blame there, and I think that Krish was going down that path, a very simple path, at the beginning of the year, and we steered him away from that and said we want to be able to go full 3D mode and know where we are in the field at all times. And I think he had the right idea of doing it very simply in the beginning, and that could have worked out a whole lot better for us if we had just stuck with his original plan for that. Another thing, let's use things that we understand as opposed to just trying to use things because they're the latest technology. So if we don't understand everything Path Planner is doing, let's not use it. Let's keep things contained in ways that we can understand them and troubleshoot them. And let's become really good at the basics and how to use them really well, and build up that toolbox of skills and be able to solve problems with that basic set of skills, and then expand from there. So let's figure out really good motion control. Let's figure out really good odometry tracking and updating. Let's figure out basic use of vision, and then apply that to some game challenges, and then expand from there. But let's get good at the basics before we try to really start using some of the advanced stuff. So those are my big takeaways from what we can learn from 2056 from last year.